Well, good evening, folks, and thank you, and thank Facebook for hosting us. This is one of a series of talks about the Mill CPU architecture, covering quite a bit of material. That's the list of talks that we've had so far, and we are currently at that one. This covers a great range, and some people here have been following us along for years now and are intimately familiar with the architecture of the machine, and others will be quite new here, and as a result there's a bit of a problem in trying to get the levels right for a mixed audience like this. Those of you who are old hands, I hope that you will bear with me when I have to give a little bit of background explanation for the benefit of those who are not. This talk, well, if you look up there, you'll see the previous talk was interprocess communication, and talk 7 was security and reliability. And it happens that this talk and those two heavily overlap, because they make use of a common mechanism, but viewed in different ways and for different purposes. Consequently, again, certain of this will overlap with the prior material, but I'm hoping that you'll be seeing it in a way that you had not seen before, even if you had in fact attended those talks. And all of the talks and the videos, they're all public. The NDA that people had to sign here is a Facebook NDA. It's not a Mill Computing NDA. And you will find pretty much everything you want to know in general detail at our website. The talk is necessarily going to be intended for a general audience. You'll have plenty of opportunity for questions at the end. The Mill itself is a new architecture. It's a general purpose CPU architecture family, a family in the sense that the 360 was a family. It offers a substantial power, performance, and area, which is price and cost in the chip business, advantage over existing architectures, and why that is true is explained in great detail in those talks. This particular talk is addressing issues relating to threading, which, if you have any experience with the OS component that handles threading, or a language like Go that makes use of microthreads, you'll know that existing architectures are somewhat unforgiving when you want to do something interesting with threads. This talk explains what we provide and is the basis for an operating system or something like Go. The talk in particular will cover how the hardware threads are started and how they are dispatched, what the interaction is with protection, how cooperation and preemption work in this hardware environment, and I'll touch a bit on exception handling, which winds up being critical for a reasonable implementation of threading. The instruction set architecture of the Mill is extremely different than the architectures that you are familiar with, that you have been writing code for some time, or for those of you who are on the hardware side, have been arranging gates for some time. It is a massively MIMD, that is multiple instruction, multiple data machine. Each cycle, the high-end family members can issue 30 different independent operations. This is not SIMD, this is not vectorization. These are independent operations. Loads, stores, adds, subtracts, what have you, all mixed, and up to 30 of them at the high end. There is a massive quantity of horsepower at the high end. It is statically scheduled. There is no out of order. It's an exposed pipeline. Everything is timed. The hardware is arranged so that you start an operation and the results pop out just when you need them, courtesy of the compiler, or your hand code for that matter. And it has integrated vectors in that every operation on the machine works simultaneously for both vectors and scalars. You do not have a separate set of vector registers. You don't have a separate set of vector operations that you have to reach into assembler or intrinsics to get at. You just add, and it works just fine whether you're adding a vector or adding scalars. Lastly, those of you who are involved in compilers know what static single assignment architectures are. And in many ways, if the mill can be seen as a hardware version of an SSA machine. I'm not going to explain SSA if you're not already familiar with it. However, while that takes care of the adds and subtracts and so forth, in fact, most machines, most applications spend a very large amount of time in the operating system, and operating system overhead is a critical factor. On the mill, the operating system is in fact an application, just like any other application. They are all managed together, and they are all have the same operation set available. There are no privileged operations. There's no supervisor mode. And the protection is done entirely by address in memory, and its protection is by byte addresses. So you do not just protect by pages. You can, one byte, bingo, you own it and you don't. That works. Now the talk here will be a gross oversimplification. It's intended for a general audience, not only you folks, but all the people who will be seeing the video and looking at the slides on our website. And we have a extremely surprising to me amount of people worldwide who have been through some of that material. The reality of the machine is more complicated than the way I'm explaining it. If you are personally aware of the complications, I'm sure you'll realize when I talk about something that it doesn't really work like that. But feel free at the end of the talk to ask for details. Details are available. Anything you want to know, we'll tell you in more detail than you really want. But for the general talk itself, it has to be aimed at not quite so deep in detail. One last step, what I'm describing is hardware. This is mechanism. This is how the hardware works. It does not describe policy. There are many possible ways that you can organize a piece of hardware in order to do something, but most of that is policy. It's the distinction between what makes Unix Unix and what makes Windows Windows, and what makes both of them different from an embedded machine that has no OS at all. The mill itself is a general purpose CPU. It can run Windows, it can run Unix, it can be an embedded machine with no OS at all. It is specifically, however, it is not a Unix machine, and it's not a Windows or whatever machine, and it's not a C machine or a Java or whatever machine. And what it attempts to do is provide a hardware platform which is sufficiently general, powerful, and performant that you can do any of those on this platform, better than you can on existing architectures. Now, but to turn to threading, we realized fairly early on that we wanted to provide better threading facilities. And the underlying philosophy behind that is that we wanted to make it transparently usable, such that somebody immediately, or they can wait until later. Immediately, so that the threading facilities would be such that the people who implemented the runtime systems or the operating systems and so forth would find it congenial and easy to bring up their software for the people who would to use it for applications. So it must be unobtrusive, understandable, and cheap, or it won't get used. So now to the topics. We all know what a thread stack looks like. List of frames. Every time you call a function, you get a new one. They need link pointers internally to track which function to return back to. Your return address pointer and the downstack link typically, more in some systems. And it's a fixed size stack, so you can get stack overflow. And those links are easily corruptible by return-oriented programming or something like that, and welcome to Exploit City. The mill, as an alternative, has a secure stack. There is a second stack. The conventional data stack is split in two. One stack holds all your data, and one stack holds all the hardware's knowledge about what is going on in the data stack, including the call and return sequences. The mill has a hardware unit called the spiller, which manages that call stack. It is not in the user's application's address space. Instead, it is managed by the hardware with occasional assistance from the operating system if we need additional memory or something like that. It is inaccessible to the application programs. And the data stack is all range checked. If you've ever had the experience of a wild address in which you return a pointer to a now exited frame, you know what a pain it is to find that. And in fact, all the references into the data stack are range checked against the current top of stack, so that if you actually do that, you will get a hardware fault on a mill, rather than having to run Valgrind in order to find it on your own. Interrupts, traps, and faults. An interrupt, of course, is an external thing. A trap is a resumable event, and a fault is a non-resumable event in our terminology. In fact, in the hardware, these are just involuntary function calls. The hardware gins up a function call, but otherwise, from the viewpoint of the callee, it is indistinguishable from a normal call, and in fact, you can call handlers just by normal function calls, as well as having them invoked by the hardware. The hardware vectors to the entry point, supplies arguments appropriate to the nature of the interrupt, fault, or whatever. There is no duplicated state. In many machines, you have one complete set of registers in another state intended for the interrupt handlers and a different one for the applications. That has its costs in power and area. The mill doesn't do that. There's no task switch. The interrupts and so forth happen inside the currently running thread, and we don't have to flush the pipeline because the spiller takes care of saving everything and restoring it later. There's no restart penalty because the spiller is taking care of that. If you ever actually measure the time to get into and out of an empty interrupt, you know that this is something you don't want to be doing very often. For us, it's the cost of a normal function call. The total cost in particular, well, you will typically be mispredicting because you weren't expecting to take this trap. And of course, you have to get the new code out of your cache, but that's the only delay. Processes. A Unix process has an ID, 72 there for an example. It has some resources, memory usually, other files, open file descriptors, what have you. It'll have some permissions which give it access not only to its own stuff, but maybe to other people's stuff. And it'll have at least one thread. But a process is a software construct, and mill is hardware. Consequently, we split the process concept and did not attempt to implement process, which is too complicated, as a hardware entity. Instead, we split off the pieces which could be done in hardware. In particular, we split off the permission side, and you have hardware permissions rather than software permissions. We split off the thread side, and you have hardware threading. and the resources and administration and management involved in the process is left for software. The collected split-off permissions is called, in our terminology, a turf. It is a set of memory permissions, not necessarily memory you own. Own is a process concept, not a mill hardware concept. But it is a place that you have the ability to access without faulting. It's a protection domain, in other words. If you're familiar with it, you can also think of them as being access control lists, although it's not implemented like that. It holds the permissions for a collection of memory regions and provides cheap memory isolation. A turf is not a process. It is just the permissions. It doesn't have any associated threads. And threads are not bound to a turf the way threads are bound to a process on for example, a Unix system. So instead, a thread runs in a turf, one turf at a time, and it can change from turf to turf, so that it has this set of permissions now, and later it changes, so it has a different set of permissions, can access different things. So if that is the whole address space, and turf 5, for example, has a collection of region descriptors saying, oh, you're permitted to have access to this part and this part and this part in the whole address space, along with associated permissions. Can I read it? Can I write it? Can I execute it? And there's several others as well. And in addition, a different turf, 17 here, for example, has a similar set of permissions. Note that permissions and the region descriptors can overlap. They do not have to be disjoint. And even when they overlap, they can do so with different rights. It's just a collection of permissions. Furthermore, when it is possible for two different turfs to have region descriptors and associated permissions for the same portion of the address space. A thread runs in a turf, one turf at a time. A thread can see in use, when in this case, when it's running in turf 5, it can see those. And when it's running in turf 17, it can see those. But it can only be in one thread at any given, and in one turf at any given time. But several threads can be in the same turf at the same time, and when they're doing that, they're sharing the permissions and can share whatever the permissions are for. The threads also have a unique and non-forgeable ID. The hardware creates the IDs. And what's actually happening is that there are system tables equivalent to the TLB tables, except they carry only permissions and not paging information, with lower bound and upper bound, which are byte bounds, and they have writes and the turf ID that corresponds to this. At power up, because obviously this kind of a system means that you have to be able to, when you power up, you have to be able to access the whole machine. So the hardware creates magically a turf which contains one descriptor for all of the 60-bit address space with all of the possible permissions. This magical descriptor is called the all turf, and in fact, your vision increases as you approach the all, which is a marvelous quote from Swami Satyananda that is directly applicable to us. A portal is like a function call. Note that we have our two stacks there. On the left is the secure stack, which contains the linkages. The right is the data stack, which is visible and available to the application. Any call and return operation operates on both stacks. And I'm showing as different colors in the data stack that we have switched from one turf to another turf, from the yellow to a buff turf. So a portal call is exactly like a regular call, except you also can switch turfs. This is done in a secure way. I refer you to our other talks explaining in detail how this actually works and how it is done securely. But suffice to say that somebody who wishes to export an API will export a vector of portals. And you can call one of those, and when you do call it, the hardware will transit you through out of your current turf and do a normal function call into the turf of the person who created the portal vector. You can call in between them in any order. You can re-enter turfs, callbacks are possible. So for example, if we have a separation of concerns here where there's a network stack which is running in turf 17, and there's a decrypt and private key holding turf in turf 20, and the private key people want to make very sure that no code running in 17 can access the private keys. Well, we'll start out with, say, thread 9 running in turf 17, excuse me. And it will then call decrypt, but except that decrypt is in fact a portal. The result is that the request passed through the portal and went over into turf 20, like that. You're still in thread 9, but you've completely changed your permission environment. And in particular, you now, because you are in turf 20, have access to that private key. Eventually, that operation, because after it has been appropriately decrypted, the operation will return. And a portal returns just like any other function call. But because we have all of this information in the secure stack, we realize that, we got here via a portal call, we have to unportal ourselves on the way back out. And that, in fact, is what's happened. And we're now back in turf 17 with the results of the decryption, and the two are kept in complete hardware isolation from each other. Now, you can think of the turfs and threads as being a two-dimensional structure. A portal call lets you switch turf quickly, but in addition, a dispatch operation, which is in hardware, lets you switch thread quickly. Time to talk about dispatch. Each core is running one active thread, one at a time. Other threads are parked. They are marked in such a way that the hardware knows that it is not currently running. The dispatch operation, which is an executable op like an add, activates a parked thread and parks the thread that did the dispatch. So it acts like a coroutine. Control is passed from one thread to the next. This is not a privileged operation. We don't have privileged operations. Any turf and any thread can do a dispatch operation. The spawn operation, which will be touched on later, starts a thread and dispatch resumes and transfers between them. You can only be active on one core at a time. So how that actually works, assume that thread 3 over there is active, and after having done a portal call, it's now currently running in turf 9, having formerly been in turf 3. The active is green to draw your attention to it. Meanwhile, there is also a thread 12, parked, indicated by the orange there, which has gone through several different portal calls, but is currently also in turf 9. it does not matter that they've been through several protocols. The only thing that matters is what is the current one. And you can then do the dispatch. So the dispatcher and dispatchee are required to be in the same turf. We've now switched. Now 12 is active and 3 is parked. That's what the hardware does. Later on, you'll get into some detail about how that is actually implemented in the hardware, giving you an abstract view at this point. Now, a protocol lets you switch rather quickly, so you can think of that as being a rank and file chess move. And the dispatch operator lets you change threads. But night moves are not possible. You cannot simultaneously change both turf and thread, because this would break the security model. A brief digression on the subject of concurrency versus parallelism. This is a distinction which is not widely made, but winds up being quite important in this topic. Concurrency is when things can run in overlapping time periods, whereas parallelism is when you have more than one actually happening simultaneously at the same time. The concurrency is what these threading facilities provide. Parallelism on the mill is provided by having multiple cores. So all of this talk is dealing with concurrency, not with parallelism. Cooperative multi-threading is one of your standard ways of doing this. Those of you who date back to the early Apple days will recall when the Apple OS was cooperative. Is there anybody no? Never mind, you're all way too young to know anything about that. It is also the mechanism used behind for things like Go routines in the Go language, or at least it was the last time I looked there. And generally has an overwhelming advantage in that it's cheap and fast because the OS stays out of the act. So let's assume that what we've done is we start a Go routine to fetch an URL. Well, you spawn a new thread to do that for, and you dispatch to it so it can make the I/O request, and of course it's not there, so it immediately blocks on the I/O. So the runtime system must dispatch to another runnable Go routine, which will spawn yet another one, and so on. This is a coroutine-like style. You have one thread of control which gets passed from one thread to another thread to another thread. This is cooperative multi-threading. It's a lot like the stack switching that you have for lightweight threads and Go routines. The major difference is that it is secure on the mill. And there's no problem if you want to call things like syscalls, whereas most cooperative multi-threading things, if you make a syscall and block on the system, then that shuts down your entire collection of threads rather than just the one that you're in. That does not happen in the mill hardware threading. It is concurrency and not parallelism. Preemptive, the kernel sets a hardware timer. When the timer fires, the kernel handles the interrupt. It does so in a kernel turf, as the interrupt transferred into a portal which got you into the kernel turf. The kernel has a run queue of people to execute, and the kernel decides who to dispatch to next. This is not a choice of the person who got interrupted, it's a choice of the supervisor or the runtime system or operating system. It is preemptive, and it is not up to voluntary good behavior on the part of the applications as it is in cooperative. Blocking I/O is similar. A thread will make a syscall, perform some blocking I/O, If the buffer is empty, then the kernel will find another thread to run, and eventually it'll wake up again when the buffer becomes available. Preemption I have to go into in some greater depth. Cooperative is fairly obviously, you just dispatch to each other and keep track of who you want to dispatch to. But preemption is more complex. Let's assume that we are in thread 6, that thread 6 is active and it's currently in turf 9. The kernel, as before, sets a hardware timer. When the timer fires, the core looks into the trap handling vectors and that are in place for the current turf. We are currently in turf 9. Different turfs can have different trap and what have you vectors. In this case, the runtime system and the vectors will have been set up so that it is pointing to an operating system handler, and it will be a portal so that the interrupt is serviced in a kernel turf. So we now have a kernel turf on top of the other two, and the code is actually kernel code with kernel privileges at this point. Note that I am describing policy. This would be a representative implementation. That the setup for that is entirely software. This is not something the hardware is doing. Now, the kernel does have a ready queue, and it decides who to dispatch to next. And let's say it decides that it wants to dispatch to thread 4, which is, of course, parked. It now does a dispatch. Now 4 is active, and 6 is parked. The magic here is that the black code is exactly the same code. That is, what the state of 4 is where it was when it got dispatched out. And now it's being dispatched back in at exactly the same point. If you're familiar with set jump and long jump, you have a similar situation in which control will return to a point that you have been to before. So the handler here is one function with a dispatch in the middle, and sooner or later it will get control back and then proceed to execute the rest of that handler. So the magic here is that is exactly one function. Those are not two different functions there in black. That's one handler in which half of it is done on the way out and half of it is done on the way in. The kernel puts the parked thread, the thread it used to be, into the ready queue, suitable for the next time that somebody is going to pass control back to it by being preempted, and resets the timer and returns back to the application. We're done. Now for the machinery underneath the hardware. The spiller stores the privileged state and the machine state for purposes of doing returns in the secure stack, and the secure stack is kept in a data structure called a spillet. Say that's a spillet. Because you get a new entry each time a call is made, there will be entry and entry and entry and entry going up and down with the calls. Note, this is not the data stack. This is a hardware maintained secure stack. If you fill up a spillet, we trap to the OS, necessarily switching to a different turf because otherwise we would still be overflowing this one. And the OS grabs us another one for a heap, and we link to that. And if necessary, we link again. There is one spillet per thread, And we find the spillet because it is always at a calculated address based on the thread ID number. We reserve a portion of the address space such that there is one spillet for every possible thread. And how many are possible? Well, that is the number of bits in a thread ID. So that if there are, say, 16 bits in a thread ID, then there's 64K possible spillets, and there is a vector at a known location which corresponds to the address space where these spillets will be. There may not be a spillet because many threads will not exist. But if there is such a thread, then its spillet is at a known address. Stacklets are similar to spillets, except they deal with the data stack. A thread needs to have space for its own data stack. So when it makes a portal call, it will wind up having a new stack. This will not be frames on top of the old stack, because the old stack the caller can still see. And the whole point of security is that the caller cannot see the callee, and the callee cannot see the caller when you go through a portal. So, in fact, the way for the hardware to do this is you have two stacks, one for everything that's happening in one turf, and one that's for everything that's happening in the other turf. So, when we make a portal call, a new stack is created, a new data stack is created. And if it makes another portal call, it gets yet another. The logical stack of the thread working its way through all of the portal calls is, in fact, a chain of stacklets, each one associated with this thread and a particular turf. So whereas the spillets, there's one spillet for the thread no matter where he goes, in the stacklets there's one per thread per turf. Again, these are at fixed calculated addresses, and I'll show you how that works. One stacklet per thread per turf. If that's your application, the WKR register, that stands for well-known region, is a hardware lower bound, upper bound, which describes the live portion of the physical stack. This is how we ensure that if you attempt to address to dead data because you have returned a pointer to what used to be a local, this is how we are able to detect that that is now illegal, and you will get a trap for accessing dead stuff. And the WKR register holds that information, and it is checked. If the application portal calls a service, well, you get a stack frame in a new stacklet, and now because you're in that one, the WKR register now describes the active portion of the new stack. One of the jobs of the spiller is to switch the WKR register, so it's always save and restore the WKR register, so it's always describing the live portion of the current stack. If a service backcalls the application, you get a new frame back on the original stack because we have now returned to the turf that we were in before. And indeed, the application can recall nested back into the service, and it will get a new frame there. Note that the WKR's range has been expanded to accommodate the additional frames. All the frames in any given turf and thread are adjacent. But this leaves a hardware implementation problem. How do you successfully allocate a stacklet in the middle of a portal call? I mean, this is just a function call. You're not going to be running out and grabbing memory. Well, they're not allocated in memory. They are allocated in address space. In particular, they're statically allocated in address space. One big whopping big array In fact, for the stacklets, 1/16 of all of the 60-bit address space is reserved for use as stacklets. If I zoom in on this, they are laid out as a two-dimensional array indexed by turf and thread ID. Zooming in, I see that I was looking at thread 17 in turf 36. And if I zoom in on that yet again, there is our stacklet. This can be computed directly from the IDs. We do not need to do any computation. So that finds us where the stacklet should be if there is one. The stacklet is addressed in this way. If we are in 17 and 5, that will be its address. The F on the left says that we are at the high end of the address space. And the 4-4 is actually a bit offset of the value 17, which is the thread ID. And the 5 is the turf ID, and that computes the address of the stacklet. When we portal, everything is the same except the 5 is turned into 9, and we're now addressing a different stacklet for its computation. Protocol uses address space, not necessarily memory. Because in hardware, any address space that is not had allocated memory is implicitly 0 in hardware. The way this actually works is that if you do a load operation, well, first we check to see if you have permissions to access it. Well, that's fine. We'll assume you pass that. And then we send the load down the memory pipe, and we get to the L1, and we look and say, do you know what this thing is? And the L1 will say, not me. And you go to the L2, and does the L2 know what you mean? And the L2 says, I don't recognize this. And you go down to the TLB, and it looks up in its tables to get a virtual to physical translation. And the TLB says, I don't know anything about this either. This must mean that it's 0. And without having any memory out there at all, the load will simply return to 0. So anything that you don't know anything about, you get back a 0. Well, this is mighty convenient for a number of ways. It means, among other things, you don't have to sit there and be 0 or memmove to initialize all your data, because it's automatically already 0. And the whole mechanism behind that, which is a good deal more complex than I'm describing, is available at that URL. I encourage you. Callbacks, of course, form an issue. If we are just automatically going and using that calculated address, when we did a callback, we go and use it again, and we proceed to use the same address for 2 different purposes, and that won't work very well. So if we make a portal call to 9, and if that calls back, we're going to wind up using the same space, which is an oops. The solution is the stacklet info block, which is logically you can think of as being in a separate computed address location, and I believe some of the members will probably do it that way. In other cases, we just use the bottom end of the stacklet, the low end of the stacklet, as the info block. And it's a cache line size, and it holds a bunch of metadata, which includes the top of the stacklet information. And the values in it are offset in such a way that If there is no stacklet there, that is, if this particular thread and turf combination has never before been used, then all of the values in the info block will be 0. Well, guess what happens when the hardware goes to look for the info block and it doesn't find it? It goes all the way to the bottom, gets an implicit 0, it comes back up and says, oh, okay, this is clean and I can use it. If, on the other hand, the load to get the info block pulled up random bits, oh, this is in use, find the offset to the top and park my new stuff there at the top. This means that we do not have to initialize those things. They are already initialized for free with zeros. The portal call writes the current stack range and a whole bunch of other information into the stacklet and into the secure stack. And because empty is all 0, unback loads are implicitly 0, so an unused stacklet is empty. The result is that a portal call costs 2 fetches. We have to fetch the portal itself because that tells us where we're going to go and what its thread is going to be and various other information. And we have to fetch the info block in order to know what stacklet we're going to use. But other than that, it's the same as a function call, and that's why the overhead is so low. Creating a thread, the spawn operation. It's also not a privileged operation. Any turf can spawn. The new thread is initially parked in your turf, so that if we were in turf 17 thread 9 and we do a spawn, we will still be in turf 17 and some new thread number, 15 in this case. That number is hardware allocated. You do not tell the spawn what the thread ID you're going to use. Instead, you just say spawn and it'll find one for you, and you wind up getting the number of the thread you just spawned back that you can use and keep in your data structures for later dispatch work. When it's resumed, somebody dispatches to it. The thread is entered as if the function that you gave to spawn had just been called as a perfectly ordinary call with arguments. Stack fragments. The hardware manages the call stack securely. The data stack, you can tromp all over it as much as you want. It's just your data. The stacklets form a chain with one stacklet for each turf versus thread combination. The spillet, there's only one of for the whole thread. We call the sections which are of contiguous turfs fragments, and the corresponding call stack things, although they are adjacent rather than separated, we also call fragments for terminology. If we have to unwind an exception, say that top frame had an exception, it doesn't matter if it's C++ exception or something else, sooner or later the hardware is going to become aware of the fact that an exception had occurred. If it is a software one, the software has available to it operations it can call to trigger a hardware exception. So the hardware manages that. So let's say that we got a bye-bye in that top thing. We will then, that is a fault which the software can have a handler activated. And if the handler is the C++ runtime system, it will do the normal C++ call the destructors, yada, 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 as it works its way down. Eventually, however, you'll get to the bottom of the fragment, which is the point at which somebody portal called into us. Now, we cannot let a C++ or anybody else's exception cross a portal, because the guy on the other side of that is not expecting to get an exception come back. So instead what happens is that the hardware flags the same turf's next fragment, that is the yellow one below the light blue one, to say that when control reaches here, throw that same exception again. And the guy in between does not get a fault. He gets a trap that tells him that the portal you called just got in big time trouble and you better clean up whatever you want. But it's not his fault. So that's why he gets a trap rather than an unrestorable, unrecoverable fault, which is what the guy who got in trouble is going to get when the light blue actually does exit. Now, sometimes you have hardware that is complaining that you did something which is a naughty no-no in the hardware, like an illegal operation or something like that. But you also need to be able to trigger this from software. Welcome to the Hey You operation, which can be emulated. It causes the recognition that a trap must take place in the topmost fragment of the same frame, so that for example, if the light blue does a Hey You to this thread, then the interrupt does not happen in the topmost. It happens in the topmost of the same frame that the Hey Youer was in. So this is how you can get a Hey You happening in the middle of your stack, and nothing happens until control works its way back down to that point. This solves the problem that you would have if, for example, your target thread has called some a big library, which is often in a different turf, and the library doesn't know what to do with the KU. That's not its business. So it completes in a normal fashion, and only when it returns is the Hey You delivered to the target turf. And the necessary marker is over there on the call stack, so that because the call stack is secure, as we work our way back down, we'll find it. However, if the right frame, if the right turf is currently actually is the top, you'll get it delivered immediately, of course. But if it's not, we wait until we get down to it, as soon as it's unwound to. Threads die. It may have entered many turfs at the point where it dies, possibly more than once. The turf doesn't own the thread. It shares the thread with all the other turfs that the thread has been through. So when the thread dies, we cannot automatically kill the turf because other people may be using that turf. A thread can invoke death upon itself with the suicide operation. And it works very much the same way. Effectively, it's a non-catchable fault that will work its way to the bottom. Think kill -9 in Unix, if you're familiar with that. It will work its way to the bottom. However, unlike kill -9, the intervening steps belonging to other turfs will have an opportunity to recover their state, which kill -9 doesn't let you do. The data stacks can be reclaimed. As things unwind, this pillar stack winds up being also reclaimed. Eventually, you'll get to the bottom, and the whole stack that can be discarded. Well, folks, this is one rather small aspect of the machine, but one which would be very vital to people writing operating systems and runtime systems and language systems. Clearly, there is a movement for parallelism, for threading. Clearly, that has gotten steadily in trouble because of intractable bugs and conceptually intractable problems trying to make use of them. What we're trying to do is give hardware that provides a clean and natural and not bug-free, but easier to make less buggy platform for software. Here's where you go if you'd like more info about any of it. The mailing list has a relatively low rate. Primarily, it's used to announce talks like this, and the docs will give you many hours of great joy if you go through and watch all the videos. I'm open for questions. The gentleman in the back had one earlier.
You mentioned that Linux and Windows are on this. Were you able to deploy Linux unmodified?
Can you repeat that for me?
You mentioned that Linux and Windows can run on the new hardware.
Okay.
Have we done Linux?
We're in the process of bringing up the necessary runtime system. Linux is not yet running. It will be quite a while before it is. That is a major task. It is on our calendar, and unless we wind up with a customer or partner who demands us to do something else, we expect that Linux will be, in fact, the first OS on it.
Is there a mechanism that makes it so that you have exactly one operating system on it?
Dave, can you repeat
Is
for me?
there a mechanism that makes it so that you can have exactly one operating system on it?
As opposed to
As opposed
supporting
to
also
many
Windows, for
other
example?
Because you said that the OS is just an application.
It's whatever code you put on it. I mean, this is hardware.
In other words, are you asking, can you port something yourself? Is that,
No. So normally the OS assumes that there's one OS.
oh, can you have
That's why
two
it
OSs
has,
that you go back and forth
privileged
between?
permissions, right? That makes it so that you have one.
Well,
There's a whole bunch of assumption around the idea that there's one OS and not seven.
well, if what you're talking about is virtualization, yes, the hardware does support virtualization. It is. I'm not sure I would want to try to write an operating system which shared non-virtually its space with a second operating system. Sort of by definition, whatever code that comes up in the all at Power Up is the operating system. That's what it is. But we do have code that does that, but it's primarily for hardware verification and other such things. It is running without a separate operating system, but you can think of it as that is the operating system.
It's like a supervisor. So you don't have reads, right? So, but in the other words, don't you have like unlimited number of reads? You don't have read 0 or read 1, read 3.
There are no rings.
There's no rings.
There are no rings. All protection is based on what would be the TLB on a conventional system, except that it's byte granularity, and there is the operating system is the same as any other application, except it has more regions with more rights.
So is it like a multiple number of rings, in other words?
No, you can. There's tens or hundreds of thousands of turfs available in the turf ID space, and each one of those has a unique set of things it's got rights for. You could mimic a ring system by having, in fact, only 3 turfs with their respective rights. And some software portal mechanisms, though, you could transfer from one to the others, but it's not intended to work like that.
So if you can only dispatch to another thread parked in the same turf, does that mean that if an application spawns and dispatches to a thread to cooperatively to go off and do something, and that thread then blocks on I/O in the kernel or device driver turf, the operating system can only then dispatch to some other blocked thread in the operating system, not back to the originally
You can-
part
you-
thread?
There can be multiple nested dispatch systems. The simplest one, which is alluded to here, is that you may have a cooperative system running within a application, and above that a preemptive system running in an operating system. But there's no restriction to this by having two levels of that.
But you're saying the kernel turf couldn't dispatch back to the cooperatively parked thread in the application because it's in a different turf? Or?
It can. The kernel would dispatch back to a ready-to-run thread who is in the kernel's turf. Now, the way the lower level system, if it didn't want to have the restriction of having one that blocked, when presumably you don't want that, what the runtime system for something like Go would do is at startup it would spawn half a dozen things which did nothing except give up control to the operating system. And when the operating system wakes one of them up, it then looks around in the Go level and does a dispatch to that. These are in effect a pool of lightweight processes. Yeah.
It's sort of implied that you have a fixed number of hardware threads. Are those actually swapped out, or is that a hard limit?
The number is determined only by the ID size.
But once you reach that, you're done.
Well, this is once you run out of process IDs on Unix, you're done too. I mean, it's.
You implied sort of a 16-bit number there. It's not a very large number.
It's a large number. Running out of IDs, before you ran out of IDs, you would run out of physical memory necessary to keep all the structures that you would need to keep track of what the IDs were doing.
Does that mean at some point the spawn instruction would fault into the operating system and say, hey, we run out of thread memory, and it would be able to
if you ran out of IDs, but the IDs are recovered. I mean, the idea that you would have several 100,000 simultaneously active threads, different family members can set the ID size to whatever is wanted at configuration time. Yes, you can run out. You'll have bigger troubles if you run out. You had to run away. Yes?
How is a turf reclaimed, and under what circumstances is it reclaimed? How is a turf reclaimed, and under what circumstances is it reclaimed?
Both turf creation and turf reclamation is a software process. That is because it has to have the things that it has rights for granted to it, and only the software knows what this new turf is supposed to be able to get at. So that is fundamentally a software process. We do threading, we don't do in hardware, we don't do turfing in hardware. The turf is effectively, as an early slide showed, something that is a resource management system aspect which is left to the software.
So does that mean that any thread can create a new turf or destroy them if there aren't any threads that are left in that context?
No. The ability to create a turf is essentially privileged software. There's tables in memory that the hardware uses to keep track of all of this stuff, and you set one of those up when you want to create a new turf. This is essentially what the linking loader does when the shell. Typically, everything that would be a process in Unix, each one of those is going to have its own turf. And there's a vast quantity of administrative arm waving, setting up quotas and everything else involved in creating something like that. And We leave all of that to software.
So does that mean to kill a process, effectively you wipe out its turf information and the hardware would just throw faults on all its threads? And
The-
die?
The hardware only cares about the IDs. The IDs and what permissions are associated with it. Yeah.
I'm sorry to be Mr. Linux today. Is there a performance implication that's dependent on the number of regions that are in the turf?
No limitation.
And is that sort of swapped in like a TLB?
There is a protection look-aside buffer
Right.
that handles all of that. Not mentioned here, but covered extensively in the memory talk. The mill is a SAS system that the caches are in virtual, not in physical. That is sometimes called a single address space system, which is what SAS stands for. And so, as a result, the TLB, that is the translation to physical, is after the caches and does not get banged on very often. And the only thing that's in front of the caches is the protection side, which on a conventional system does both translation and protection in one step in front of the caches. We do the translation after the caches, and there is a substantial win as a result of doing that, because it can be much bigger and much slower because we're almost never banging on it, whereas the protection mechanism is in front, and yes, there's a PLB. Yes?
Turf permissions. In the previous presentation, you mentioned read, write, execute, and some other permission sets. Can you give us some examples of what those might be?
The other ones?
Yeah.
Well, one of them is the ability to re-grant a permission. Somebody gave you a permission. Can you give it to somebody else? Again, covered in the other talks. Yes, in the back.
I didn't see any reference to something like simultaneous multi-threading. There's something like that.
Yes. This is a different notion of threading than what I'm talking about here. SMT, simultaneous multi-threading, is a hardware mechanism in which the hardware switches back and forth between two sets of machine states, typically your register sets, and it does so fast enough that you can, if you have to go to DRAM, you can steal a few cycles for somebody else in the meantime. We don't do that, or at least in the current configuration.
Like switching between the two, that's not typing two hardware, two threads running simultaneously, right?
Well, this mechanism would work fine whether you're doing SMT or not. This is a different level of discourse. The reason why we do not anticipate doing SMT unless we wind up getting seriously into the mainframe business is that it turns out that the cost of the extra state, the duplicated register banks, and all of the necessary things in order to route potentially two completely different sets of information into the machinery is sufficiently large that it's cheaper to just have a second core. So we don't do SMT. Instead, we'll give you two cores.
But being a statically scheduled machine with 30 wide, it's going to be pretty wasteful for most real applications. You're just running a single thread.
Surprisingly little, and the kinds of applications you're going to run a high-end machine on, you're going to keep you're just banging on the computational units real hard. That's for a application, for example, something like what the Z series of IBM, a large-scale mainframe commercial system where you're getting memory misses all the time because the data structures are big databases and they're much bigger than the caches. And so you're getting data misses all the time. There's a reason why IBM is 6 wide SMT as opposed to 2 wide SMT. That is because they're missing in the caches all the time in their kind of workloads. And if we had those workloads, we'd do something like that too. But for the kinds of general purpose workloads. We anticipate that in fact it's cheaper to have a second core. The power that goes into a core is not in the computational units. ALUs are dirt cheap. You spend the overwhelming amount of your overhead is spent figuring out what you're going to do next, getting everything ready to be able to do it, and then doing something with it after you've done it. The actual do is a tiny amount of the work and the tiny amount of the power. Now, this is heavily dependent on your workload. And because the mill is a family, we will be tuning for particular application market areas in different ways. But for the broad middle range, we're not expecting to do SMT. We've run the numbers, and the numbers say give them more cores instead. Yes?
So if I wanted to run some mill software today,
yes,
what could I do it on? Is there an emulated system that is available, or some hardware?
Well, the first thing you have to do is go to our website, and where you see it says join us, and you sign up there, and then you have access to everything, and you can use it to your heart's content.
What's available? Like, is there an emulator or?
There is and has been for quite some time a picosecond accurate simulator.
Okay.
The tool chain is, well, pre-alpha, I will put it that way, but we do stuff with it. And our next major milestone will be a FPGA implementation. That is merely a proof of principle. It's not intended to be a product.
And so I think you said something about the mill architecture is going to be much more performant from a per watt perspective. And so how do you come up with the kind of the numbers that you're quoting there, like tens of times?
Well, we sort of pull it out of our sleeves, actually. Collectively, we have a vast quantity of experience, and when you're talking 10x, the fact that we're going to be off by 0.3, we don't especially care. We can tell what the performance per cycle is because our simulator and the code is sufficient to tell. And we know what things a conventional out-of-order machine spends all its power and area on because we've done them. And we know that we don't do it that way, and we have a very good idea of what the area and power ratios are going to be. As a rough, again, very much of a rough thing here, for equivalent cycle and process, and for the same amount of compute capacity, the same number of ALUs, the same number of this, the same number of that, we expect that we will be running about 40% of the power used for a conventional out-of-order machine for that, and run probably slightly above 50% of the area of that. So you've got roughly a factor of 2 in power and factor of 2 in area for equivalent before you start looking at better performance.
Sorry, so you said for the equivalent process, so what else is there? So you get this 40% of the power, 50% of the area, and then...
A factor of 2 in each, roughly.
Right, okay, and then the rest of the speed up, or the rest of the performance gain is from what? I'm missing something.
The rest of the performance comes in 2 ways. One is the sheer width of the machine. We have found that, in fact, there is much more available instruction-level parallelism than is widely thought, and I refer you to the discussions on the belt and the execution talk, which explains why we get a ILP of 6, whereas everybody else gets an ILP of 2. And by all means, go look at it. a more recent talk on switches actually gave some code examples with this a little test program got dropped on our forum by somebody who didn't understand the explanation of how we did switches, and this is a switch with 10 different cases, and some of the cases called functions, and they returned values, and they did random stuff. We cranked it through our tool chain and came up with a program that did the entire switch, all of it, including all the cases, in 3 cycles on our mid-range machine, the Silver. We were real pleased until a different one of our readers, looking at the code that it generated, figured out by hand how to do it in 2 cycles on the same machine. I encourage you, the code's there, you can go see how it works.
Compared to a DSP.
Compared to a DSP. It happens that most DSP-like work tends to be all carefully tuned in assembly language, if necessary, so as to that everything's working all at once and there's no misses. And we are the kind of code you get out of us and what you expect to see looks very much like DSP code, handwritten, but you don't handwrite it.
And DSP performance per watt.
Oh, the performance per watt is very similar to typical of that of DSP work. If you're used to the performance per watt of the laptops you have in front of you, and compare that to the performance per watt of most of the Internet of Things type DSP work, they're easily getting a factor of 10 power performance gain over a conventional general purpose. One of the things we said all along about the mill is that what you're going to get is the power performance of a DSP against general purpose, not handwritten code. We take perfectly ordinary code off the Internet and run it. Now, of course, if your code contains embedded intrinsics for the AVX or something like that, no, it's not going to work. But software lock-in is alive and well in the Valley. Yes?
Just very briefly, how satisfied are you with the current state of the compiler and mining the ILP out of these general purpose codes that you're running?
We're quite pleased with it. It is buggy.
Yeah.
Trying to, we use the Klangen LLVM front and middle ends, relatively unmodified, and our own complete from scratch custom backend. We do not use the LLVM backend structures. It has been an interesting process because at least my own prior experience, I've done a bunch of compilers, but they were always have been for register machines, and this is not a register machine, and it took a little figuring to figure out how to do it.
But you generally keep the width, all the various slots fairly well.
Well, it's easy to write something which is just a long chain of dependencies,
Yeah,
and we're not going to do any better than anybody else. But one of the things that studies on available ILP have found is that there tends to be quite a bit of ILP, but it's a long ways away.
Just locality wise.
It's a locality issue.
Around loads and
around loads and what have you, and it appears that the out-of-order machines could, in fact, do a much better job if they could get the decode buffer windows up into the 500 or 1,000 range.
They just don't have as much scheduling.
They don't see far enough. We do static, and yes, it's easy to have code that is not exposing this, but it's also, if it's there, we find it. The other thing which is a big win for us is that things which are very expensive on a conventional machine are very cheap for us. that those call ops. That's a one-cycle operation, including all of the save and restore and everything else. That's a one-cycle operation. You call, that's one operation, that none of the arm waving around it. And you look at typical general purpose code, it's overwhelmingly call heavy. You're doing a call every 5 instructions. And, well, if that call is in fact going to be 7 instructions in order to handle the call protocol, and it's 1 for us, well, you're looking at a nice big factor just there. Another aspect has to do with the load dependencies. Statically scheduling works for things which have fixed latency. The canonical thing that does not have fixed latency, of course, is loads, because you miss in the caches. And we have special facilities in which we are able to launch a load long before we need the value. And we are free of the possibility of right after read hazards or collisions, so we can hoist a load over an intervening store whose target address we don't know. And the hardware handles that.
You're saying because the cache is consistent.
You will see our loads retire the value which existed in memory at the point when they retired, not when the load was issued, but when they retired. It makes a big difference. See the memory talk for how that works.
One more question. You talked about 1 cycle calls. How many cycles for a thread switch?
Well, the dispatch op, you're going to have a couple of reads of memory in there, so 2 or 3 reads of memory, and the actual execution itself is 1 cycle.
So we talked a lot about memory, but I'm not clear. Do you have virtual addresses? So it's
Yes, it's a virtual memory system.
So it's virtual memory. So how do you guarantee protection? Do you flash caches?
How do I guarantee?
So you only do checking, right? When you reach TLD, and at the same time, how do you guarantee that?
The virtual memory system is a single address system, so there is no aliasing
On a single core.
on a single core.
So what about multiple cores?
Also on multiple core on the same chip. We do not extend the single address off chip, but you can have as many cores as will fit on the chip. You've got 60 bits of address space. That is an awful lot. Even with you've got 64 cores on that chip, all running nice big programs, you're not using 60 bits of address. Consequently, we can just simply pack it in. Very early machines also had single address spaces, but then they had to stop because the application demanded more memory than would fit in the address space. The application is using a gigabyte of stuff on a 32-bit address space. Well, you can run 1 of those or maybe 2 of those, but you're sure not going to run 14 of those because there isn't enough address space. Well, with 60 bits, that changes things a little bit.
Yeah, but all your addresses, basically your default memory model is like the largest memory model. So every address is assumed to be like 60 or 64 bits, right?
The addresses are 60 bits, not 64 bits. The remaining 4 bits have their own usage described in some of the other talks. But the addresses are 60 bits, and that goes all the way down to the TLB where they're translated to physical addresses. And what the physical address size is depends on how many pins you have on the bottom of the thing.
So, since we're in danger of losing this room pretty soon, we should probably wrap up questions here, but I'm sure we can all find some space to answer any more questions. I'd like all of us to thank our speakers today.
And thank you. And I'm happy to give you excruciating details in the hall outside.
To be fair, we may not lose the room, it's just
Oh, should we stay here
Officially-
until we do?
Yeah, we can stay here until we do.
Oh, we'll stay here until we do, folks.
Like-
Those of you who haven't already had enough.
Yeah. Officially, we may be kicked out, so we'll see.
Okay, well, they can throw us out when they want to.
Exactly.
What happens when you run out of stacklets?
You don't run out of stacklets.
Of a single stacklet. You try to like dump 2 gigabytes into your stack. Should you just like never do this?
No, you can. The stacklets are a fixed size, and the hardware detects the fact that the next allocation is going to be too big for it, and will trap. And the handler for that trap will turf switch, so you're not using the same stacklet. And it will then presumably allocate something from a pool of available space it's maintaining, and do the necessary, set up the necessary links, and the handler will then return, and you didn't realize that you overflowed your stacklet.
So it would be a special, larger stacklet.
Yeah, whatever. That's policy. It gives you whatever it gives you.
So is a stack a linked list of stacklets?
It's a
and you
link.
just
It
end
is.
up
It is.
copying your turf?
It is a linked list of stacklets, and when you overflow the last one, somebody will get a trap into a handler who will produce the next one. Yes.
Question. So, I've been following like what you're doing, and as I understand it, like the FPGA you said is in the works, but you guys have started off, as you described it, with a simulator, right? And the specification piece. And this is
We've
all
been at it for a while.
right, statically scheduled, down to like, you've described how the cycles are all very tightly interwoven. How are you budgeting, like, what is going to take how long when you have not yet gone to hardware? What is that back and forth like?
You mean how long the individual ops take? What the latency is? Well, basically, we expect that they'll take the actual execution. An ad will take an ad time, no matter what.
Okay.
And we do juggle across the family members this a little bit. Thus, for example, as currently configured for the machines that do support quad, that's 128-bit arithmetic, that it's configured in the specification that all the software works off of, that's going to be a 2-cycle ad, whereas a 64-bit ad is a 1-cycle ad. And this determines the clock rate that the hardware guys have to do. Now, as the hardware comes up, they'll kick back and say, well, gee, I thought I can do a 64-bit ad, but that's winding up being the clock critical aspect, and so why don't we make a 64-bit ad be a 2-cycle ad, and or do we juggle it someplace else? And that's just the typical hardware refinement process. All of the timing and the simulator and the software is driven by a specification machinery in which 2 pages of spec of what a particular configuration looks like. You put it in, you turn the crank, and half an hour later you have a compiler backend, an assembler, a simulator, and a bunch of other software, and the stuff that drives the RTL for the hardware guys, all mechanically generated. We commonly in CPU design, one of the first things you do is you lay out the bits of the instructions. We've never looked at the bits of the instructions for years, because the actual bit layout is mechanically generated to be code optimal for entropy reasons, and the individual binary instruction sets are extremely compact.
So that sounds novel. Do you think you're the only people who really fully operated in that manner?
Well, there are other systems. The ARC system is a configurable system for the embedded market, which you can change the number of registers you have and things like that. But they are not doing it with mechanical generation. They do it by having a whole bunch of reserve things that our customers can plug things into, a whole bunch of things in the instruction set architecture, in the binary. Position encodings which are not otherwise used, and their customers can use for whatever the customer wants to put on their chip, because they sell custom chips. We don't do that. We will sell custom chips if somebody wants us to, but instead we do not have a preset binary encoding. Instead, there's a binary encoding unique for each individual family member, and indeed for each individual encoding slot within a family member. It has its own unique binary encoding, which is all mechanically generated. Yes?
So if I understand correctly, right, there's one address space per any number of cores on a single socket, right? And then the TLB is between sort of all of that and the memory bus.
Exactly.
What about running machines with multiple sockets, and how would that be working?
We expect that you will be using message passing between sockets.
I see. Okay. So
That's
like NTI style?
Whatever you like. We feel that the trend is away from super large shared memory in the supercomputer business, is what you're describing.
Okay.
And maybe we're wrong, but that's a business decision, and we could, if we were to go and add another 20 bits to the addresses, which we could do, then we certainly could get enough address space to handle, all of Facebook and without any trouble. They're just bits, and it's just address space. It's not like it's real memory.
You mentioned the spawn call was unprivileged. If the operating system or the kernel wanted to restrict the number of threads or processes that could be spawned by a particular turf or processor user, is there a way to do that? Or
this is an example of the general problem of quotas.
Mm-hmm.
Most operating systems maintain a quota system, going back to the days of how many pages could you print with a line printer. The mechanism for enforcing that is currently we have not yet put in. We know exactly how we will do it, but essentially it will be a per thread or per turf, more likely, set of access constraints. And the way it will work is that there will be an MMIO location, and whenever the spawn operation goes, it will proceed to ding that one down, and if it hits 0, you've got a trap, and whoever it was that set the limits will catch the trap and do something nasty to you. We know how we'll do it. We just haven't bothered putting it in the sim yet.
So does the kernel have a way of tracking how much time has been spent by each thread in each turf, or even which application, which turf created the thread in the first place?
Well, actually, in the hardware, because one of the things that the hardware guys have to do is they have to be able to monitor the execution of the actual underlying hardware. And so there are, as is typical of chips, there are facilities in which a whole lot of things can be monitored and get routed off chip for instrumentation. The degree to which any of that wants to be exposed to an application, well, guess what an exploit loophole that would be.
But the kernel might want to know.
Hmm?
The kernel might want to know, though.
Well, do you trust the kernel?
The CPU schedule and things like that.
Do you trust the kernel? I sure don't trust modern kernels. The mill is designed to throughout to be for a microkernel architecture in which the true trusted software is 2 pages of code. Yes, you can run a monolithic OS on it without any trouble, but it's designed so that you don't have to do that, and you will get, in fact, not only a lot of security, but no cost overhead, as is typical with the microkernel, where you have to switch in and out in order to do the task switch.
But ideally, wouldn't the CPU scheduler have a good idea of exactly how much CPU each application has been using, so it's making a decision who to schedule to next?
It can keep track of all of that. The question is, do you want to do it on a per thread basis, or on a per CPU dispatch basis, so that if below you Go is going back and forth, bing, 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 and cooperatively multitasking, Is the OS care whether one of those or another had more?
You'd probably want to account it to a turf, wouldn't you?
No, because the Go was presumably all in one turf. It's one application, one turf, and doing cooperative multi-threading within that turf. But fundamentally, the underlying machinery is there. The question is, would you find it worthwhile to keep track? Would the OS want to be tracking Go threads? Probably not. It doesn't now, to the best of my knowledge. Yes.
So, in an ideal situation, you talked about bringing up L4 or whatever, you have a true micro kernel-based Linux or whatever running on the mill, fully making use of turfs as protection layers. You've given the example before, like an image decoder in a browser is running in a separate turf, right?
You bet.
Something, if that was constructed, you mentioned the possibility of an insecure kernel. Would you have the ability to then run your application on an insecure kernel with all the turf barriers in place, feel secure in what you did in that application?
You will feel more secure.
Okay, sure.
There is no such thing as true security. There's no security which is proof against money and cute girls. Okay?
Fair enough.
So what we've attempted to do is actually to improve the security, but to a very large extent what we've attempted to do is to help you catch the place where you did something dumb. Thus, for example, I mentioned several times here that we will catch if you return a pointer to dead space. Well, you're not supposed to. It might be a security hole, or maybe just somebody being able to browse in what had been the rubble left behind by the last function call. But for sure it's wrong. Mm-hmm. And we do tell you, and we tell you a whole lot more than any other system out there. Yeah, it would improve its security, but it don't make it perfect.
As far as trusting the kernel, if the kernel has the all turf, it can read all your memory.
Yeah.
Unless it gives it up.
More?
I'm out of paper for my notes.
Folks, are we done?
Turn this off.
There will be another talk, probably February-ish or something like that, on vectorization and wide data and how that works in the hardware. This is this particular talk is very heavily high level and OS interfaces and things like that. But when you get down to vectorization, you're doing nothing except banging on the bitsies. And so if this one was too high level for you, come to the next one.
Do you know where the next one will be?
Do not yet know. We've made use of, we've been welcomed by, and thank you Facebook again, quite a few different venues, and different people have a space available for a talk at different times. We'd be happy to come here again.
Thank you.